This will be another long lecture, but I think a fascinating lecture. And in electromagnetics right now, this is probably one of the hottest areas, and enabled by metamaterials, in fact. The first thing we'll do is start out talking about coordinate transformations. That's where the magic is happening. We are going to define some kind of coordinate transformation that in this transformed coordinate system, our fields would bend in some prescribed manner, some way that we want. Then we transform the coordinates of Maxwell's equations. What we'll see is that Maxwell's equations have something called form invariance. In other words, they look the same no matter what coordinate system we're in. So when we transform the coordinates of Maxwell's equations, that lets us pull the coordinate transformation out of the coordinates and sort of suck it into the permeability and the permittivity. And now we have our ordinary Maxwell's equations back, but we have this crazy map of the permeability and permittivity. At that point, transformation electromagnetics is done, probably more commonly called transformation optics. But that's done, and then the whole next step is, well, how do we realize these very crazy values for the permeability and permittivity? And that's where the metamaterials comes in. That's what lets us do this. One of the first big exciting things that was done with this at Duke University was cloaking, and they actually demonstrated at microwave frequencies that an object could be cloaked. This can actually work. One of the issues is that these involve very extreme parameter values, which implies the use of metals. Well, there's a push to do the same thing, but with just dielectric structures. And one of the first ways that this could be practically done is with something called carpet cloaking, where you have an object up against an infinite conductor, or up against a carpet, if you will. There's a whole bunch of other applications that I'll step you through, and we'll make some concluding remarks, and that will be this lecture. We have to start out talking about coordinate transformations. There's a lot that could be said on this. As I am with all my other lectures, I will say the bare minimum so that you can develop an intuitive feel of what's happening here. So using a coordinate transformation, we really can map from one coordinate system to another. So our original coordinates we'll just write as a standard vector. When we map it with some mapping function t, we use this prime superscript to indicate that's our transformed coordinate system. So we can have a first Cartesian coordinate system, if you will. Here's how we would write r. And here's a similar looking coordinate in our transform system. And if we were to plot where the original points are in the transform system, well, we could get any crazy looking thing. And we design our coordinate transform so that this crazy thing that we get in the end is how we want our fields to bend. The big thing that we are going to make use of to transform our coordinates is something called the Jacobian matrix. And in fact, the Jacobian matrix doesn't really perform a coordinate transform, but if we have functions that are a function of position, and we want to transform them into a new coordinate system, that's when we use the Jacobian. So the Jacobian is not directly doing a coordinate transform, it maps functions, it transforms functions between coordinate systems. So we'll call it A, and a three-dimensional world, it's a 3x3 matrix. And if we look at the elements, we can actually interpret what's going on here. We'll take this top one. We're really talking about how far a coordinate in our transform coordinate stretches or displaces relative to a similar change in the original coordinate. So in other words, this is sort of like an amplification factor, or a stretching term, if you will. And essentially it compares x to y, y to z, z to y, and all the different combinations. So imagine if we move a point a little bit in our original coordinate space, what is that equivalent movement in the transform coordinate space? So I envision it as stretching. Anyway, we call this the Jacobian matrix. We'll make extensive use of this. I have a bunch of examples of how this is used as well. First example, let's say we want to calculate this Jacobian matrix to transform operations from cylindrical to Cartesian. Remember, we're not actually transforming coordinates. We're not taking position 1 and figuring out position 2. we are calculating a Jacobian matrix that would transform a function from cylindrical to Cartesian coordinates. So in general, this top set of equations is how Cartesian and cylindrical coordinates are related. And so this is really telling us how we can differentiate these and see if we change x by a little bit, how much do our cylindrical coordinates change. So here's how our Jacobian will be defined. Remember, in the numerator are the coordinates in the transform system. In this case, that's Cartesian. And in the denominator are the original coordinates. In this case, it'll be cylindrical. So we go term by term. And this top one, dx dr. So dx dr will go up, and we will differentiate this equation. And we end up with dx over dr just equals cosine theta. Anyway, we go for all 9 terms and just differentiating these equations and getting all these elements. Once we have all these answers, we plug them back in and we have our final Jacobian that we would use to transform functions or operations from cylindrical coordinates to Cartesian coordinates. Example number 2. Let's say we're going from spherical to Cartesian. Slightly different set of equations. These should be familiar. We define our Jacobian this way. Again, in the numerator are the original coordinates, and the denominators are our transform coordinates, r, theta, and phi in this case because we're in spherical coordinates. Well, we calculate all these derivatives, and we look at these equations to do that. And if we work through the math, here are the 9 elements of that Jacobian matrix. Then we plug in our answers, and here's our final Jacobian. And this Jacobian would transform a function or operation that is currently in spherical coordinates into Cartesian coordinates. Last example, Cartesian to Cartesian. So maybe we're stretching an axis or something like that. So that's pretty easy, and these are just the stretching factors. So we can actually transform from one coordinate system to the same coordinate system, but maybe it's just scaled. Now, so we have a good grasp of how we can use this Jacobian, or how we can calculate the Jacobian. Let's think about how to use it. So if we have a vector function, the electric field, for example, that is a function of position. So we have the electric field in our original coordinate system, and maybe we want to find the electric field in the transform coordinate system. So we're using the prime superscript to represent the transform coordinate system. Well, if we know the Jacobian, we can do this very easily. A is the Jacobian. And we can rearrange this equation and bring the electric field in our original coordinate system over to the left, and it's just the transpose of the Jacobian times the electric field in the transform coordinate system. So if we can find the Jacobian, it's real easy now to transform these vector functions. Let's think about how we use this to transform operations now. So here, f is an operation. This is different than an electric field. An operation is something like a derivative, an integral, a convolution, a Fourier transform, something like that. It's not an actual electric field that we might think is more of the answer to a problem. This is an operation. So if we want to transform an operation, it's a little bit more complicated equation, but we still make use of the Jacobian. And it's the Jacobian times the operation times the transpose of the Jacobian divided by the determinant of the Jacobian. And now we have that operation in the transform space. So in Maxwell's equation, we have the curl operators, and we'll be doing this to the curls and the derivatives and stuff like that. This section may be a good example of how we apply the Jacobian to Maxwell's equations. Functionally, this is really just to show that Maxwell's equations are form invariant and how we apply a Jacobian to it. So Maxwell's equations are form invariant. This means they are independent of the coordinate system that they're in. So for example, what do Maxwell's equations look like in Cartesian coordinates? Well, they look like this. What do Maxwell's equations look like in cylindrical coordinates? Well, they look the same. What do Maxwell's equations look like in spherical coordinates? They look the same. What do they look like in some strange Martian coordinates? Well, they look the same. So no matter what the coordinate system is, Maxwell's equations look the same. So here's an important consequence. If we have Maxwell's equations that we've transformed to a new coordinate system, we can pull the math doing the coordinate transform into mu and epsilon. And we end up with a new set of Maxwell's equations that look like our original Maxwell's equations, but the coordinate transform has now been pulled into mu and epsilon, so we end up having a pretty crazy map of mu and epsilons. And in fact, one of the drawbacks of transformation optics or transformation electromagnetics is that we have these crazy values, and sometimes it's very difficult to realize those. And we'll see that later in the lecture. So remember, we have different ways to use these Jacobians. Well, one is how we transform mu and epsilon. In Maxwell's equations, it turns out that mu and epsilon are more accurately described as operations. The unknown here are the fields. And when we have epsilon times E, for example, we're actually multiplying epsilon times E. So we have the permittivity operating on the field. So the way we transform our mu's and epsilons is through the second way that we talked through of how to use the Jacobian, where it's a little bit crazier equation, but this transforms operations. And remember how we define the Jacobian. So here's a quick proof that Maxwell's equations are form invariant. So we have an original equation, and when we transform the coordinates, we have coordinates inside our del operators. We get a prime superscript, another prime superscript on E and H, and then of course a prime superscript on mu. So here's how we write Maxwell's equations in our transformed coordinates. But you'll notice it looks exactly like it did over here because of the form invariance. So let's prove this. Let's define a coordinate transformation this way. We have an r prime operating on our original coordinate. So we have three things in this equation to write in terms of the original quantities. We have our electric field, we have our magnetic field, and we have the permeability. We'll leave the del operator untouched from now, and you'll see what happens there. So this is how we transform functions, and here's how we transform operations. So now what we're going to do is plug these into the original Maxwell's equation. Here we are doing that. Here's the original Maxwell's equation. Here's our two ways of using the Jacobian, but we have three terms. E and H are transformed as functions. The permeability is transformed as an operation. Well, if we substitute all those in, we end up here. If we turn our algebra crank on here, we can end up at this form. And notice all these Jacobian terms ended up grouped around our curl operator. So do you recognize this form? Well, it turns out, remember, this is the equation we use to transform an operation. Curl is definitely an operation. So in fact, what we've done here is really, that's just our curl operator in the transform coordinates. So in fact, now we can write Maxwell's equation this way, which is what we were trying to show. We went from our original Maxwell's equations, applied our coordinate transforms, and we ended up here. And that equation looks exactly the same. So Maxwell's equations are form invariant. That's key to transformation electromagnetics. Here's a simple example of the proof that I think is a little bit more intuitive. So here's Maxwell's equations. Let's say our coordinate transform is a simple scaling. We will amplify all of our coordinates by a factor of a. So here's all of our terms. Here's our curl operator. Here's our terms in the transform coordinate system and our curl operator in the transform coordinate system. So right now, this really is the only place where we see a, and it's stretching the coordinates. Well, it turns out we can take this 1 over a and pull it out of the curl operator, so it was over here, and we can bring it over and apply it to mu. And we can always do that. We can always pull our coordinate transformation out of that curl operator and put it into the permeability or permittivity, depending which of Maxwell's equations you're working with. So again, here we are back to the original Maxwell's equations, but we're scaling mu instead of the coordinates. Electromagnetically, that's the same thing. So here we are. All of transformation electromagnetics will come together in the next 10 slides for this simple example. And at the end, I even show you some MATLAB code that you can use to generate the equations describing the permeability and permittivity and how to visualize it. In my mind, here's how I envision transformation electromagnetics, also called transformation optics. I envision it happening in 3 main steps. So first, we start with our original coordinate system. And in our original coordinate system, we just have rays or lines that are just straight. The next thing we'll do is define some kind of coordinate transformation such that this line gets perturbed, or group of lines, and they'll get bent in some way that we need, that we think is desirable. At that point, we do our transformation electromagnetic stuff. We put our coordinate transformation in, we absorb that into the permittivity and permeability, and what we come out with is essentially our original coordinate system. But now, in place of having warped coordinates, we have a permeability and permittivity in the background. And what we see is this ray will now refract. Instead of bending due to a coordinate transform, now it's bending due to refraction, but it bends according to the same way. And that would be our device design in 3 easy steps. First thing, we need to pick a coordinate system. And there's no recipe for this. We pick the coordinate system that will simplify the math to describe your coordinate transform. And it's really up to you as the engineer or scientist here to figure that out for yourself. But it's whichever one works the best, whatever would simplify the math. But in principle, any coordinate system will give you the same answer if we don't make any mistakes. So for simplicity and clarity here, let's choose Cartesian coordinates. And we also choose a background or a starting permeability and permittivity. So let's just start with free space. That's pretty common. And we have our standard Cartesian coordinate system. And notice that I've drawn these horizontal lines. That would be the field lines, if you will, or the direction of a wave. So we're in our original coordinate system. They're all going straight. The next thing we need to do is define some kind of coordinate transformation that would bend those lines in some way that would be useful to us. So for example, maybe we want to squeeze a wave through a little tiny hole. And so what we would need to do is pinch these lines together, and maybe there's a hole here. We're squeezing as much of a wave through that as we can. And so here's our coordinate transformation to do this. X, Y, and Z are the original coordinates, and with the primed, those are the transformed coordinates. And we'll use these equations to fill in the Jacobian, and then we'll apply the Jacobian to the permeability and permittivity. Now we calculate the Jacobian. I'm repeating these 3 equations. I'm not repeating the definition of the Jacobian, but we know it has 9 elements, and here are the derivatives for all 9 elements. And we're just taking derivatives based on these starting equations. So for example, dx prime dx we get by differentiating this first equation. The harder ones, for example, are the dy prime dx, and we have to go in here and take the derivative with respect to x, and then there's a second one where we take the derivative of this with respect to y. So we come out with 2 sort of bigger, uglier equations, but all the others are pretty easy. Then we plug these answers in, and we have our Jacobian that we can use to transform our coordinates, or transform the functions. And ultimately what we want is that crazy map of permeability and permittivity that results from this coordinate transformation. Now we're ready to apply this. We have our Jacobian. We have our starting permeability and permittivity. Remember, that was just free space. We apply our Jacobians to it, and we come out with crazy mu's and epsilons. In this case, they'll be the same, because we start off with mu and epsilon being the same. We're doing the same operation with the Jacobian, so our permeability and permittivity will come out being the same. So in fact, whatever we write for the permittivity, will be the same for the permeability. And if we work through the math here, remember mu's and epsilons are tensors. These Jacobians are also tensors. When we work through the math, here's what we end up with. And I'll admit I didn't do this by hand. I used the symbolic toolbox in MATLAB, and I'll show you the code that I used here in the next few slides. But here's what the tensor would look like. And so permeability and permittivity are the same thing. They're 3 by 3 tensors, so they're visualized in that same order. And this came straight from those equations on the previous slide. If we plot those, this is what they look like. So in principle, if we could come up with a permeability and permittivity that look like this, then we could pinch our fields. So here's the MATLAB code using the symbolic toolbox. The first thing I do is I declare the symbolic variables. I define the starting permeability and permittivity. So I just creates an identity matrix. So we're starting with air. Then we define the coordinate transform in terms of these symbolic variables that we created up here. And Sx and Sy are these sigma variables down here. And so xp, yp, and zp, those are our primed coordinates. So that's our coordinate transformation symbolically. Then we construct the Jacobian using the diff, which calculates derivatives symbolically. Once we have the Jacobian, then we can calculate our expressions for our crazy UR and ER. And remember, those will be equal. So in fact, it's a little bit wasteful to calculate the same thing twice. So in practice, you would only do one of these lines of code. So let's say we did ER. We have the command pretty, which is part of the symbolic toolbox in MATLAB, and it displays the equations, the equations in this 3 by 3 tensor in pretty form or best looking form. We can look at it and actually see equations. So that's it. That is transformation electromagnetics in MATLAB. That is pretty darn simple. So here's some MATLAB code that would follow what we have on the previous slide to visualize the tensors. Or maybe we're constructing arrays in finite difference frequency domain or finite difference time domain that then we would simulate. So the first thing, we have symbolic expressions inside big ER. So we'll substitute in actual specific values for sigma x and sigma y. Then we set up a double loop over our grid where we're drawing our permittivity and permeability. So for each point, we will substitute the actual coordinate value in for x into ER and the actual coordinate value from y into the point y in ER. I'm using little ER here because I don't want to overwrite the symbolic expressions in big ER. But now we have actual numbers here. There's no more symbolic variables left. And this will be a 3 by 3 tensor, and then we write that into our point in the grid. And then when we're done, we're ready to visualize all of those, and that's what we saw 2 slides ago. Now, I want to talk you through really what I think made transformation optics, transformation electromagnetics famous, and that is cloaking. Sir John Pendry and Smith at Duke University applied transformation electromagnetics to design a microwave cloak and actually demonstrated this was possible. So in this section of slides, I want to step you through their design process that they used. I think you'll find it quite ingenious and quite simple in a way. First, what is a cloak? Well, we have an object that we want to hide, and that object would scatter waves if we would let it. So instead, we surround it by something that when a wave is incident on that object, or at least that something surrounding the object, it would manipulate the wave in such a way that on the other side, it perfectly reconstructs that wave as if there was no object or anything present. That's really, really important that it reconstructs that wave. It can't create any kind of shadow zone. Simply not reflecting is not invisibility because we could be looking on the other side. And so it has to completely reconstruct that wave front. The famous cloak was a cylinder cloak, and it obscured some object in the middle. And think about what has to happen here. We have a wave in air that travels away from the object, but another portion of the wave enters our cloak region has to come around and then back out again. It has traveled a farther distance than the portion of the wave up here. So in fact, it has to travel faster than the speed of light inside the cloak in order to do that and come out in time with the field that's up here in air. And so what you'll see is we end up with parameters less than 1, leading to a refractive index less than 1 that would allow the wave to propagate faster than the speed of light. Here's the basic path of the rays that we want. So following the recipe we laid out in the previous two sections, we start off with our original coordinates and we define these rays just passing straight through. Next thing we want to do is define some kind of coordinate transformation that would bend all of these rays around the middle. So that's our goal. What kind of transformation would do that? Once we come up with that transformation, the procedure is the same of what we've just done. So in this sense, it makes sense to do this either in spherical or cylindrical coordinates. Cylindrical coordinates if we just want a two-dimensional simulation. If we really want a three-dimensional object, then we would do this with spherical coordinates in 3 dimensions. Another thing that we're defining here is 2 radiuses. We have this inner radius, R1. That's the radius of the object that we're hiding. We have this outer radius, and that will be the outer radius of our cloak. So our cloak stuff, our metamaterial stuff, will be in this region between R1 and R2. Outside that will be air, and inside R1 will be the object that we're trying to hide. So here is that coordinate transformation. And the coordinates theta and z, we don't do anything to, but the radius function, here's our coordinate transformation. Not too bad of an expression. Well, then we fill in our Jacobian, and here we're transforming from spherical to spherical coordinates. We've just done something with our radius term. And what you'll see is what we've done is we've compressed the radius between R1 and R2. Anyway, we calculate all the terms of the Jacobian and we fill it in and it reduces to this. And this is actually the simplest Jacobian that we've seen yet in this lecture. Now we start with a permeability and permittivity in free space. We apply that Jacobian to it, and this is where we end up. This is our final permeability and permittivity tensors. They're both the same. We would call this tensor diagonally anisotropic. Now let's plot those. We only had 3, so we just have to plot those 3 diagonals, and here they are. Now, this is a great example of some of the drawbacks of transformation electromagnetics. We have some very extreme values here. At the center of this, we have the permeability and permittivity approaching infinity at the center. For the other 2 tensor terms, we have it approaching 0 at the center. But we spend a lot of time with the parameters being less than 1. Well, remember, that's a necessary condition because we need the refractive index less than 1 in order to have waves that travel through the cloak come out in phase with waves outside that are traveling a much shorter distance at the speed of light. So that makes sense. Well, here's the actual cloak done at Duke University. So imagine here's the cloak and here's the map of the permeability and permittivity, and they designed metamaterial unit cells to give the correct permeability and permittivity, and here's the design, and this is really a uniform lattice in cylindrical coordinates. As we mentioned before, one of the drawbacks about designing devices with transformation electromagnetics is that we get rather extreme values for the permittivity and permeability. Well, there's one case where we can get around that and actually think about making all dielectric structures. And so the first one that really made this famous was carpet cloaking, although people are working in other areas now. I guess I'll mention on this slide that The extreme values for permeability and permittivity are more serious at optical frequencies because the metals are much more lossy at optical frequencies. So at microwave, it isn't as much of a problem, although still a problem, but certainly at optical frequencies. Carpet cloaking is when we have an object up against a ground plane and we want to bounce a wave off of that. And if the object weren't there, it would look like it's just bouncing off of a mirror. With the object there, that would tend to scatter. So in terms of the coordinate transformation, we are essentially taking that object and squishing it down to zero size. Based on that, we can identify three cases for carpet cloaking. We can squish an object down to a point, we can squish an object down to a line, or we could squish an object down to a sheet. So this sheet is really what we're going to be talking about with carpet cloaking. There's a little bit more limited because it's a carpet cloak, it's up against a ground plane, but we can actually realize these cloaks without nearly the extreme values, and our materials can be isotropic, and in fact we can do this with dielectrics. Here's the carpet cloak concept, and throughout this section I'm really just going to be hitting the high points. I strongly suggest reading the literature for the details. I'm just going to hit the high points here. But what essentially is happening is we have some object hidden under some kind of cloak. And so imagine up here, in comes a wave, and it would hit this cloak. This cloak would do whatever it needed to do, such that the reflected wave looks like it just bounces off a mirror. And it acts just like this, where we have a homogeneous material and a mirror down here. And so if a wave hits this, it would just reflect. That's called carpet cloaking. The limitation is now we're up against a ground plane or some kind of mirror. We have our Jacobian, and we're going to define something new called a covariant matrix. And our Jacobian is defined the exact same way. The covariant is the transpose of the Jacobian times the Jacobian. So we'll be using that in this new formulation. Here is what we'll call the original coordinate system. This is where we have our effective material properties, and we can have any dielectric constant we want. We'll set the permeability to 1 because we don't want to have a permeability. We'd like to do this with dielectrics only. So this is what we want our system to act like. So a wave that is incident in this system, being homogeneous up here, any wave that's incident will just bounce and get reflected. So when we cloak our object, we want it to behave like this. Well, now here's our object. We put our object up against the ground plane, but we wrap it in this cloak that will do something magical. And we need to figure out now what is the mu and the epsilon needed to do that. So it comes down to this. We look at this as a coordinate transformation, and in our homogeneous system, if you will, the dielectric constant can be anything. We're going to set our permeability to 1. In our transform coordinate system, things are a little bit different, and we take this reference dielectric constant, divided by the square root of the determinant of this covariant matrix, and mu is the Jacobian times the transpose of the Jacobian divided by the square root of the determinant of the covariant. So this is what the mu and epsilon would need to look like given whatever our coordinate transform is, which gets built into the Jacobian and then to the covariant matrix. Here's how we would calculate the mu and epsilon from that in this case of carpet cloaking. At this point, based on how we calculated the permeability, it was still a tensor quantity. We don't want that. That means it will be more complicated to realize. But waves have two polarizations, so it will see, really, depending on which polarization, 2 values from the permeability. So we'll call mu t and mu l. And what we're going to say is that mu t times mu l has to equal 1. So these don't individually have to be 1, but we're going to say that their product has to be 1. Well, if it has two different permeabilities, it makes sense that there's two different refractive indices as well. Well, we can characterize this anisotropy using the ratio of these two different refractive indices. So we can take NT over NL or NL over NT. We take the biggest one and we'll call that the anisotropy factor. Now, we want to pick some magical coordinate transform. And if we do that correctly, it turns out that we can ignore the permeability. And here we'll just set our permeability tensor to all ones. We calculate our dielectric constant the exact same way. So the magic comes in how we pick this coordinate transform that lets us ignore the permeability. Well, we have this equation at the bottom. There's a lot more that could be said about this. But essentially, we want to pick our transformation so that that big phi parameter is minimum. Now, when that happens, we end up with a pretty high dielectric constant, a high permittivity, but very low anisotropy in the permeability, and we can set it to 1. We really should say, to do cloaking, the materials need to be anisotropic. If we pick, in this case, a suitable coordinate transform, we can approximate it better as isotropic. Let's think about that. If we did a somewhat poor job and we came away with an answer that had a low dielectric constant, here's what our coordinate transform would look like. And notice how much the coordinates are waving here. So this really implies that we need a higher degree of anisotropy. Now, if we go to a high dielectric constant, what we see is less waves in the lines than we do up top here. That means this has less required anisotropy than this first case. Notice again that we have a big wave up top and a smaller wave down bottom. So less anisotropy with a high dielectric constant. We need more anisotropy for the low dielectric constant. And it's probably more difficult to get anisotropy than it is to get a high dielectric constant. So that's preferred for this case. Well, let's look at scattering if we do this correctly. If we cloak our device correctly, in which case it is here, we can see we have this bump that should scatter. And in fact, down here where we're modeling reflection just from the bump, it does scatter. If we cloak it correctly, we have a beam coming in, and we have a nice clean beam going out. So to an observer up here, it looks like this wave just bounced off of a nice mirror. If we look closely, we can see, yeah, there's something else happening here. It's not quite a clean reflection. But definitely here, without the cloak, it scatters. This little bump is scattering. So it works. This carpet cloak works. We can do it with just dielectrics, and we can do it without anisotropy. Now what I want to do is just survey a bunch of other applications where transformation electromagnetics or transformation optics can and is being applied. So one is cloaking of antennas. We might want an antenna to radiate, but maybe we don't want the bad guys to know that the antenna is there. So we might want to cloak our antenna. On this slide we have two antennas. We have antenna A1 and A2. A1 is transmitting at frequency F1 and A2 is transmitting at frequency F2. What we would like is A2 to transmit at frequency F2 and have it pass right around A1 unperturbed. And likewise, if A1 is transmitted, we'd like it to pass by A2 unperturbed. So here is A1 transmitting through an uncloaked A2. So here's A2. We see on the left, we get a nice pretty pattern. But on the right, it's breaking up the radiation pattern, and it doesn't look real pretty. Now we cloak antenna A2, and we radiate from A1, and what we see is a nice radiation pattern on the other side. Now, maybe we're hiding antennas here, or maybe this is two very close antennas on a ship that are coupled that we want to isolate, and we can sort of bend the fields around the other antenna. Now, when we design this cloak, something that we're not really talking a whole lot about here is this has to sculpt frequency F2, right? But this cloak also has to be transparent to F1 because A1 is transmitting F1. We don't want to do anything crazy in here with F1. So that does put an additional requirement on the cloak. Here's something else neat that we can do. We can make an object of one shape scatter like it's an object of another shape. For example, let's say we have a block object, but we don't want the bad guy to know that this is a block object. We want it to look like a little tiny elliptical object. So here's a source, it radiates, and here's what the scattering looks like from an elliptical object. So in this case, we don't want to make our big block, we don't want to make that invisible. We want the field outside the cloak to look like it was an elliptical object. So we wrap it in this cloak, wave comes in, it does hit the big block, but the cloak sort of reconstructs it, and what we see is a field scattered from this that looks like it was scattered from a little tiny ellipse. So if there's a radar interrogating something, and maybe it's interrogating an airplane, suddenly it looks like a bird flying through the air. And so while it's not invisible, it is disguised in some way. Well, we talked a lot about polarization splitters. We can also do this with transformation electromagnetics. And in fact, we can control the two different modes independently. How do we do that? Each polarization sees a different tensor element. And so we do a coordinate transformation differently on the different tensor elements. And now the two polarizations can do really whatever they want to, and completely independently. If we could realize those fancy anisotropic materials that we would get in the end from the design process. Polarization rotation, that shouldn't be a surprise that we can do that either. Wave collimation. So if we have a dipole source on the left, if we just let that radiate, well, we just see a nice cylindrical wave. And maybe in 3 dimensions, that's a spherical wave. Well, if we radiate inside a special slab, it turns out we can collimate that. And you'll see this sometimes for focusing radiation from antennas. Maybe from the antenna it's diverging, and we can put some kind of transformation electromagnetic lens in front of that that would then collimate that beam and give it effectively higher gain. Here's another version of that where we move the dipole source outside our metamaterial lens thing. And so dipole source radiates like a dipole with a dipole source on the outside, and it flattens. So we could actually give a little tiny antenna that wouldn't be highly directive, let that pattern pass through this lens type of device, and it could collimate that beam for us. Bending beams, we're doing a lot of that here. We are using spatially variant self-collimation to do that, but we can also certainly do it with transformation electromagnetics. So that ends this lecture. I do want to make a few final concluding remarks. So transformation electromagnetics, or transformation optics as it's called a lot of times, it's a coordinate transformation technique. And the way it works, we define some coordinate transform that would bend the fields in whatever manner we want. Maxwell's equations are form invariant, meaning we can take that coordinate transform out of the coordinates and pull it into the permeability and permittivity. And what comes out is this map of permeability and permittivity, such that if we're back in that original coordinate system again, it would bend the fields in the same way. So the output of transformation electromagnetics is this map of permittivity and permeability. It does not tell you how to realize them, and that's where the metamaterials come in. That's how we get the extreme values. Very often, though, not only do we have extreme values, we have anisotropic values. And so extreme and anisotropic, it's all more difficult to realize. And that is transformation electromagnetics.